So we continue to simplify. And sigma n from 1 to infinity 1 over n power a e power negative ib natural log n equal to sigma, like I told you, I call sum or sigma, right? N from 1 to infinity 1 over n power a. Yeah, and this one I can rewrite like this one by using the Euler form of a complex number. So you can get e power negative ib natural log n equal to cosine, cosine like this negative what? Negative v natural log of n, right? And plus I sine negative b natural log of n also. Yeah. And here negative 1, I got it into the power of n here. So after that we get like this. We get sigma n equal to 1 to infinity 1 over n. Yeah. Multiplied by cosine of b natural log of 1 over n, like this one, right? And this one I sine b natural log of 1 over n. And I here it is still imaginary unit, right? Then I expand the sum here. I mean, I use the sum, the sigma of sum is the sum of sigma. The sigma of sum is the sum of sigma. So I got like this. Here, 1 over n power a. Yeah. So I got like sigma n from 1 to plus infinity 1 over n power a multiplied by cosine b natural log 1 over n. Yeah. And this one plus, because of I is it's not an intake. Intake here is n. So I is a constant in the sigma. So we can get I out of the sigma. So I sigma n from 1 plus infinity. Yeah. And this one is still 1 over n power a multiplied by sine b natural log of 1 over n. Yeah. So we got two sigma here, this one and this one. And what we have written here? What? Zeta function, zeta of s, right? As you see, after I rewrite or simplify the form of zeta function with respect to s equal to a plus ib, I got zeta s equal to the sigma n from 1 to infinity 1 over n power a cosine natural log of 1 over n. Yeah. And for natural log here, let me call it ln, right? After in short, natural log ln, right? Yeah, ln 1 over n plus I sigma I n from 1 to infinity 1 over n power a sine b ln 1 over n also. Okay, so if you see like this, what can we get? Yeah, we get here is the real part of zeta function with respect to s, and this the imaginary part of zeta function with respect to s also. Okay. Remind you that, in fact, our goal, I want to find the non-trivial zero of zeta function. I mean that if I let s equal to a plus ib, I have to find s. Yeah, if I let s equal to a plus ib is non-trivial 0 or zeta, I have to find s. And to find s, I just find its real part and its imaginary part. It means that to find the non-trivial 0 or zeta function here, I have to find a and b. You got it? Yeah, I will use this to find a and b. To find a and b. But to find a and b, because s is a, s is a non-trivial 0 or zeta, it means that it has to be satisfied like this, zeta s equal to 0. Yeah, equal to 0. You must take zeta s equal to 0, and then you try to solve this equation to get a and b. You got it? Yeah. But before I take, or I put zeta s equal to 0, I have to simplify more about this. Maybe this can simplify more or can get a new form of them. Okay, let me find the new form of this and the new form of this, and then I will put zeta equal to 0. It means that I have to put integral part equal to 0 and it imaginary part equal to 0 also. Okay, so yeah, let's see more. Yeah, let in equal to the sum k from 1 to n. 1 over k power a cosine, yeah, b log on length over k, and then like this, and another jn equal to sum k from 1 to n, 1 over k power a sine of b log or length, yeah, length 1 over k here. Yeah, in fact this is related to this term and this related to this term, and if we take m goes to infinity in in and jn, what do we get? Yeah, and then you see like limit, you can say limit n go to plus infinity of in equal to limit n go to infinity of what? Of sum k from 1 to n of 1 over k power a cosine b length 1 over k. Yeah, and the limit, it means that you replace n by plus infinity here, so you get this one plus infinity, and you place by k start from 1 to n, you replace k by n, so this one you got this equal to sigma n from 1 to plus infinity 1 over n power a cosine of b natural log 1 over n. Yeah, in fact this one is the real part of zeta function here. Yeah, it is the real part of zeta function here. I mean that after I let in like this, so limit n go to infinities of in equal to the real part of zeta function, zeta s. Okay? Do at the same manner you get. Yeah. Do as the same manner you get. Yeah, you get limit and go to infinity of Jn equal to this, the imaginary part of zeta, I mean equal to the sum and from 1 to plus infinity and 1 over n power a sine b natural log or length of 1 over what n. Yeah, and this is the imaginary part of the zeta function here. Yeah, so you get this. So we can write zeta function. Yeah, zeta function of s equal to what? Limit n go to plus infinity of in plus I imaginary unit limits n go to infinity of Jn, right? Okay, so now let's compute in, I mean limit n go to infinity of in and limit n go to infinity of Jn. First, I compute n go to infinity of in. Yeah. Okay, I got it here to get the space for writing. Okay, we have limit n go to plus infinity of in equal 1 limit n go to infinity of the sum k from 1 to n 1 over k power a, yeah, power a cosine b natural log or length of 1 over k. Yeah. So I can tell you here to compute limit n go to infinity of in, I will use the Riemann integral definition. Yeah. And to use the Riemann integral definition, you have to choose any or some interval, and then you have to choose one partition of that interval. Yeah, then we can use the definition of Riemann integral, right? So consider the sequence of points xk satisfy the condition xk minus 1 minus xk, yeah, equal to 1 over k multiplied by square root of k. And I call this equation A. And another condition that xk satisfy is, yeah, xk minus 1 plus xk equal to 2 divided by k. Yeah, let me call this equation by B. Okay. So, yeah, sum up. Yeah, sum up. By sum up equation A, B, you get what? Yeah. By sum up these two equations side by side, you get 2xk minus 1 equal to what? Yeah, equal to 1 over k square root of k plus 2 over k. And by find the common denominator of these two fractions and do the sum of the two fractions, you get like this. Yeah, the common denominator of these two fractions equal to k square root of k. So here you get 1 plus, here you multiply by square root of k, 2 square root of k, right? And what is this? In fact, it is 2xk minus 1, yeah, equal to 1 plus 2 square root of k divided by k square root of k, right? So try to get k minus 1. You just divide both sides by 2, right? So you get xk minus 1 equal to, you can say, yeah, 2 square root of k plus 1 divided by 2k square root of k, right? And then you just separate these two terms. I mean, by the sum here, you can get this one by 2 square root of k divided by 2k square root of k, right? Plus 1 over 2k square root of k. And you simplify 2 here, and square root of k here. So you get what?